Kelvin's theorem of circulation. Kelvin's theorem of circulation. Write a heading like that. Right. It states that the rate of change of circulation is zero in a flow of fluid around a closed curve C formed by the same set of, this is very important, okay, by the same set of, the closed curve should form by the same set of fluid particles, no matter where the fluid particles are. They should form a closed loop, which should result into the computation of circulation, right? Formed by the same set of fluid particles in the flow field of a barotropic barotropic fluid. So a fluid is said to be barotropic if its density is just a function of pressure. So right, mathematically d gamma by dt is equals to 0. That is, the rate of change of circulation with respect to time is equals to 0. Call this as equation number 1. Now, what you do, you consider a fluid, consider a closed curve. First, you consider a closed curve formed by a set of fluid particles at two different instances, means time, as shown in figure below in the flow field. Okay, we just take this. Let's see if I have it. Let this be an arbitrary flow. Okay, there is no one nature of the flow. The fluid is going in an arbitrary direction. Okay, the streamlines I made like this. So these are the streamlines. Okay, now you consider a closed curve formed by set of fluid particles. Let's say fluid particles were at different locations like this. Let me just do this and draw one particle like this. So these are the, I'm going to take this as the fluid particle. So there are many such fluid particles which are forming this closed curve. Draw this, everybody. Start drawing it. Hope you all are with me.
Yes, sir.
Okay. Draw a very neat figure. It is one of the most interesting chapters of entire, what do you call, the aerospace or aeronautical engineering. Hope you have taken such particles like this. Let the closed curve be C1. First, everybody finish this. This was at t equal to 0. Can I go ahead now?
Yes, sir.
After some time, this fluid particle, like it is here, this fluid particle, let's say this fluid particle traveled somewhat like this and reached this particular location. Let's say. Okay. The next fluid particle came and occupied this position. At some new time, we are looking at this particles positions and they are forming a loop, something like this. Same fluid particle should form the loop. That is what is important. So that the mass inside that will remain the same. So this is the loop formed by, so if I draw the locus of all these points, I get a new curve. Let this curve name be C2. So the particles occupied this position at time t greater than 0. So what I do is I take the line integral of the velocity vectors. So if I draw a tangent to the streamline, or I can draw n number of streamlines like that, I'll have the velocity. So at this, I consider a particle and I take this length ds. Hope you all did that. So I took the elemental length of this curve, ds is the elemental length. Okay. Whose tangent, if I draw at this point, to tangent to this curve will be giving n cap like this. Everybody do that. The angle between these two is this angle theta. So if you integrate that v bar dot n cap ds, that is v bar dot ds bar, you get something called as circulation gamma 1. Similarly, if you repeat the process on the curve 2, you get gamma 2. So gamma 1 and gamma 2 are at two different times. Hope this is clear to everybody.
Yes, sir.
Okay. Can I go ahead now?
Yes, sir.
Okay. So by Kelvin's theorem of circulation, d gamma by dt should be equal to 0, which implies d gamma equals to 0. If I integrate this, it will become C. So gamma equals to constant. So what I can say, gamma 1 should be equal to gamma 2. Bracket it. Everybody do that. Call it as equation number 2. Call this as equation number 2. Can I go ahead?
Yes, sir.
Now let's do some Some examples will use, or you write a note. In note you write circulation in a uniform flow. Circulation in a uniform flow field. Okay, now you consider a flow like this. Consider a uniform flow parallel to x-axis. Do it, everybody. Draw this thing. Try to make it fast. So the flow is coming with a velocity v infinity, which is constant since it is uniform, and that is your u component. There is no v component. What is v? For entire flow, v is 0. Can I go ahead?
Yes, sir.
Now, you do one thing. Consider a closed curve like this. Consider a closed curve like this. 1 second. Okay. Let the name of this curve be. 1 second. Draw the dashed curve. Closed curve. Let this be A, B, C, D. Let the length of this be L and height be H. This is the closed curve C1, let's say. The entire curve ABCD is C1. Let's say you are traveling like this. To compute the circulation, you have to start from A and come back to A. Do that. That's the path along which you are tracing it. Can I go ahead?
Yes.
Right. Circulation gamma is given by the cyclic integral along the closed curve v bar dot ds bar. Since I have u and v, I will express it in terms of around the closed curve. What is the closed curve? A, B, C, D, A. It should be u dx plus v dy. 2d, right? Still it is 2d. Where v is always 0 for this flow and u is v infinity. So you can write this as this entire curve, you can write it as gamma equals to first A to B u dx. So you'll cover up this A to B. Then B to C u dx plus C to D u dx plus D to A u dx. Okay. Now you see along BC and DA. What is dx? What is dx?
0, sir.
0. There is no change in x. You are going vertically up means there is no change in x. So along BC, dx is 0. Along DA, dx is 0. Okay. So I gave the length as LH. That is the dimensions of the rectangle we have. So we get gamma equals to A to B. What is the velocity? What is u? From A to B, what is u?
V infinity.
Correct. And what is dx? V infinity is constant. I can pull it out of the integral. Integral dx, if I integrate from a to b, what I get?
L, sir.
L minus 0. L. Very good. Plus b to c is 0. Plus c to d I am going. What is the velocity? What's the velocity? You put your origin at a. Let a be 0, 0. Come on. What is the velocity from c to d? When you are going from here to here. What's the velocity, guys? Everywhere it is V infinity only. C to D when you go, what is your initial value? Final value is 0. Minus dx means final x2 minus x1. Final value of x will be what? If you consider this as origin, when you reach here, the value of x will become 0. When you are there, the value of x is L. Plus d to a, it is 0. So what do you get? Net gamma equals to 0. You write like this. Can I go ahead?
Yes, sir.
Yes, sir.
Right. Therefore, the net circulation, around a closed loop, ABCDA in a uniform flow is 0. In a uniform flow is 0. Now see what I'm going to do. Okay. Right, next subheading. Starting vortex. Starting vortex. Starting vortex and you write bound vortex. Both I'll explain in this. Starting vortex and bound vortex. Put that as a heading and write. Let's say we have a uniform flow coming like this. Fine. With a velocity V infinity. Fine. Draw this, everybody. What's the value of gamma around this?
0.
0.
At T1 equal to 0, gamma 1 is 0. Now, I'm going to superimpose this. So this V infinity, I'll put it here, which is constant. So V infinity equal to some constant C. So I'm going to superimpose this flow over an airfoil. I'm going to pass this flow over an airfoil. So I took one airfoil, kept it at slight small angle of attack like this. Hope you all are with me.
Yes,
Everybody
sir.
draw this airfoil. Draw a small airfoil like this. So when this flow comes over this airfoil, let's see what you get. What happens is when this fluid passes over this airfoil, let's say this aerofoil will experience the changes because of its shape. and the orientation, there will be changes in velocity at different points. So I'm going to mark those velocity changes. So on this surface, let's take a point on the upper surface. At this point, the velocity will become V infinity plus U1 on the upper surface. If I consider a point just below that at the same chord length, I get a velocity component V infinity. One second, let me make it okay. Right. So I get V infinity plus U2. Okay. So the velocity on the lower surface is getting reduced. On the upper surface, it is getting increased. After that, once the flow starts reaching near the trailing edge, the flow should come to the equilibrium, right? So you consider 1 point above, 1 point below. So on the upper surface, the velocity will start to decrease in order to achieve the equilibrium. Okay. So draw one vector like this. The velocity got reduced on the upper surface. Whereas to achieve the equilibrium on the lower surface, the velocity should increase. Then only it can become V infinity, right? It became lesser than V infinity. U2 is negative, you can say. So here, the velocity near the trailing edge will be the dynamic pressure near the trailing edges. So if I move these 2 points little further, if I move this point further like this, I'll reach near the trailing edge. Hope you could draw that. So the dynamic pressure on the lower surface is half rho velocity at trailing edge on lower surface square. Velocity on the dynamic pressure is half rho velocity on trailing edge on upper surface square. So obviously from the figure, the dynamic pressure on the lower surface is more than the dynamic pressure on the upper surface. So what will happen is fluid will take a curl like this. The fluid will start to curl. Draw that. So near the trailing edge, the fluid will curl. Can I go ahead?
Yes, sir.
So see, if you have, I'll show you one simulation also on the airfoil. Let me just work on it. Let me check the aerodynamics. I think I kept it. I designed this one. Yeah. Now you observe this. What is happening to the fluid particles in this region? They are getting accelerated, right? Hope you see that. The streamlines are coming closer to one another. So what is happening to the particles from here till here? The flow is getting accelerated. After that, again, the streamline started to diverge like this. Hope you could see that streamlines getting diverged. Do you see this? The area between the streamlines is increasing now. Okay. So what will happen to the velocity again? From here to there, the area was decreasing like this. And the flow got accelerated. Now what is happening? Guys, hope you are getting me.
Yes, sir.
Okay. Observe, there is a difference in this region and this region. Okay. So in this region, flow is accelerating. So here the flow accelerates. So here I would write this. Flow accelerates. And below, in this region, flow again decelerates. Many people think over the entire region, flow will accelerate on the upper surface. It is not so. Okay. The flow accelerates in a region and then decelerates in a region. Hope you see this point. In this region, you see flow is getting slowed. And again, if you observe this region, what is happening to the fluid again? The area between these streamlines is again decreasing. So flow again tries to achieve the equilibrium. Hope this is clear to everybody. Can
Yes,
I
sir.
go?
Yes, sir.
Okay, fine. Hope that made some sense to you. Now let's go ahead. Let's say after some time when the fluid particles reached over this, let's say that same set of fluid particles enveloped, created an envelope around the body with the coordinates I should have taken it slightly. So okay, let's say this is the new curve. So this is A prime, it doesn't matter, it can be any curve, but should be formed with same fluid particles. A prime, B prime, C prime, D prime, which is your new curve at time T2, which is greater than 0. So you want to calculate gamma 2. What should be gamma 2 by Kelvin's theorem of circulation? It is the curve formed by the same particles. What is happening inside is another story. Can I go ahead?
Yes, sir.
So what should be gamma 2? Tell me.
0, sir.
0.
It should be 0 as per the Kelvin's theorem. And why the flow is curling here? Why the flow is curling? Because you have
Dynamic process.
dynamic pressure at trailing edge on lower surface is greater than dynamic pressure on at trailing edge on the upper surface. So flow curls. Keep that in mind. So here flow is curling. Then it results into this entire thing. If you observe, it is also equivalent to this. This is when superimposition of this is equivalent to this. The equivalent of that I'm drawing here. So what I'm doing is I'm taking that same body here, and instead of showing velocities around it, I'm just going to show A prime, B prime, C prime, D prime. Okay. Can we go ahead now?
Yes, sir.
So what it does is it creates a the curl. So the fluid from lower surface will curl to the upper surface like this and form something of this sort. Do that, everybody. So it is curling like this. So it will create the strength of, it created one vortex. So once the fluid reaches this side, it will start to curl from lower surface to upper surface. So from the beginning, this is the first vortex that is formed. It's called starting vortex. What should be the net gamma around A, B, C, D? A, B, C, D primes? 0. But you have gamma here. Can I go ahead?
Yes, sir.
So in order to compensate, now this is the circulation in this direction. Okay. So about the center of pressure, there will be a vortex form, which will be like this. Create a vortex like this. It is a fixed, it will be bound to that location, but it will should act in equal and opposite direction to this gamma. Then only you will get net gamma equals to 0. So what is this? It is a, so the flow induces a bound vortex about the center of pressure point. This is a bound vortex. It is also called as induced vortex. Bound vortex or a induced vortex. Can I go ahead now?
Yes, sir.
Now, after some time, what happens is this bound vortex is still fixed. Bound vortex will not change. But after some time, after some more time, if you observe this, the equivalent of this after some more time becomes this. This bound vortex is still the same, but this vortex will start to become, it will become shed and it would reach some other location. I divided this into two boxes. This one is a shed vortex. Name the vortex, the shed vortex strength as gamma V. And let's name the bound vortex strength as gamma B. Gamma V, gamma V. And bound vortex is still the same. There is no change. And you cannot see this. You can see shedding of the vortices and all, but you will never see the bound vortex. I'll show you the simulation also. You will never see the bound vortex. You can sense it, but you cannot see it. So you can also name it as hypothetical vortex. What should be net gamma around this? So this becomes after some time A prime, double prime, B double prime, C double prime, D double prime, which can be broken into two different boxes, different curves. Can I go ahead? So along this curve, you are calculating gamma B. Along this curve, you are calculating gamma V. If you calculate both, the gamma V should be equal to minus of gamma B. Call it as equation number 3. Hope you all are with me. Everybody?
Yes, sir.
Yes, sir.
Okay. Hope you understood how the vertices are created and how they are related and who is who. Hope you have no doubt about starting vertex, how it got created. Everybody?
Yes, sir.
I'll show you both starting and shed vertices in the simulation, but you will not see the bound vertices, though it is getting created. You can sense it, but you cannot see it. I'll show you in one of the simulations in my virtual tunnel. You observe this. So this is my virtual tunnel. So I would like to turn this off and I'll open, let's say, a symmetrical airfoil with its geometry at some angle of attack. Okay, I took one small airfoil like this and I want the output vorticity. Hope you see when the fluid started to take place, you will see the formation of the bound vortex. After some time, that is becoming the shed vortex like that. Clockwise is taken as positive. Hope you can see the right hand side legends also. If I increase the velocity, I'll see more shedding of the vertices. And if you want to see the more rigorous pattern of the entire this street of vertices that you are seeing here behind the body, they are called as von Karman vertices. This entire street is called as von Karman vertex street. Okay, I can just slow it down to look at the nice formation of the vertices and shedding, but the frequency of shedding would reduce. So slight increment is good to see the vertices. Hope you can see that. One red, another green, one red, another green. It is like basically it is showing you the the frequency of shedding and the sign of it. Hope you can see that one green will be there and followed with the another red. Can I go ahead? So at this base, if you are observing, at this base you have that one which is forming, right? Red one, that is the starting vertex. Fine. After some time, that starting vertex is becoming a shed vertex and is going into the von Karman vertex street. Can I go ahead now?
Yes, sir.
Okay, fine. It's always good to test something that you are learning. Should do that kind of simulations. Okay, write a note now. In note you recall, we used one theorem called Kutta-Jankowski theorem. So right, by Kutta-Jankowski theorem, what is L equals to? Rho V infinity into gamma. Which gamma will be this? Will it be the starting vertex gamma or the shed vertex gamma or the bound vertex gamma?
Shed vortex.
No, it will be the bound vertex because the body is continuously producing list. So it has to be, gamma should be there. So I wrote down that. Show this like this, in this manner. Show it in this manner. Be quick. In your notes also, you write like I wrote and make that arrow also. Should never forget that it is the bound vertex. Do you see the vertex on the wing? You don't see it at about the center of pressure, but you see near the trailing edges vortices shedding. Sometimes you will see it when there is smoke or clouds, and other times you won't see it.